Okay, welcome to part 3 of 3 in this gripping instalment of 2016 AS AQA chemistry paper. If you do watch these videos, please do let me know, because I'm making them and I just think, actually, does anybody benefit from these? I get like 1 or 2 people who say yes they do, and others I don't hear anything from. So let me know if you're using these. Let me know if they're useful, because I could do with streamlining them a little bit, as you can probably tell. I'm treating them a bit more like a lesson, and maybe they need to be a bit more like a quick clip. Right, propane 1,2-diol has the structure, blah, blah, blah. It is used to make polyesters, and it's one of the main substances in e-cigs. A sample of propane 1,2-diol was refluxed. Reflux means boiled continuously with a alembic condenser with a large excess of potassium dichromate. So we've got an alcohol and we've got potassium dichromate, we've got reflux, we are dealing with oxidation of alcohols. So already, before I dive into this question, I'm going to remind myself of the oxidations of alcohols triangle, where you've got oxidizing agents, acidified potassium dichromate, primary alcohols, aldehydes, carboxylic acids. Do you know what I'm doing? I hope you know what I'm doing here, because that's all the clues here were suggesting it was going to go down an oxidation of alcohols route. Skeletal of propane 1,2-diol for 1 mark, wrong type of formula, no marks. Propane is 3 carbons, 1, 2, 3, 1,2-diol, OH, OH. If your bond goes to the H instead of the O, you get 0. You get nothing, absolutely no credit. All right? And the examiner says that on his examiner's report. You could sense his frustration when he was writing it. Write an equation for this oxidation reaction of propane 1,2-diol under reflux, using O to represent the oxidizing agent. All right. So a lot of people moan about this question because they don't know what's going on. But you're about to reflux an alcohol. Well, this is a primary alcohol and this is a secondary alcohol. So what happens when you oxidize a secondary alcohol? Well, you're going to make a ketone. What happens when you oxidize a primary alcohol? Well, firstly, you'll make an aldehyde, but if you're refluxing it, you'll make a carboxylic acid. So that's going to be your product. This is a lovely question. Write an equation for this oxidation reaction of propane 1,2-diol under reflux, using O to represent the oxidizing agent. This is a good start. Put an arrow in. All right. Then it says show the displayed formula of the organic product. So I've worked that out already. So it's going to be 3 carbons. That's not going to have changed. This will be a ketone, and this will be a carboxylic acid. Displayed formula means I need to show all of the bonds, including those on the OH. H, H, H. What happens here then? I'm also going to draw the displayed formula of the reactants. No, that's not a displayed formula. Didn't ask for the displayed formula of the reactant, but I'm going to do it anyway. Okay, bear with me. Right, I'm going to have oxidizing agents here. Okay, now this is something that we haven't particularly done much of in class. We've done about oxidation of alcohol, so here's a little tip for you. All right, if you go back to my diagram up here and we look at a primary alcohol, when you reflux a primary alcohol, you turn it firstly into an aldehyde here and then into a ketone. And to do that, there is 1 oxidation step and 2 oxidation steps. All right? So here's a good thing to remember and a nice little tip. If there are 2 oxidation steps, you will need 2 lots of the oxidizing agent. And each time you do an oxidation, you will make water. Now I'm thinking now, as I've done this is something that we didn't do anything of because this is during lockdown. We've learned this, we've done a little bit about oxidation of alcohols, but you haven't done these sorts of equations. So this is important. So this primary alcohol requires 2 lots of oxidizing agent, and then to turn a secondary into a ketone requires 1. So I'm just looking at this triangle and I know that I'm going to have 3 lots of oxidizing agent. It's as simple as that. And you will make three... Oh, no, you won't. Well, you won't make 3 waters. You'll make 2 H2Os. Why is that then? Because this one isn't right. Sorry, I'm going to go back up here. For this second oxidation, you don't make an H2O. My bad. For the first oxidation to an aldehyde and a ketone, you make a water. And for the second one, you don't. All right. I think I'm going to do another example. I think I'd have got that wrong in an exam. I'd have added it up and... All right. So anyway, if you have a little look, 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. It balances. 3 oxygens, 3 O's, and that all balances too. So if I'd have put 3 H2Os, I think I would have checked it. So if I said to you, all right, we've got this alcohol, which is a primary. Sorry, I don't know why I put that at an angle. And another primary down this end. And I said, I'm going to reflux this. Well, refluxing a primary alcohol, the primary alcohol will turn into a carboxylic acid. So you'll need an O here and an O here. So you'll need 1, 2, 3, 4 lots of oxidizing agent, 4 O's. All right. This first one kicks out water, H2O. So you're going to make 1, 2 waters. So I'll put the 2 waters on. 1, 2, 3, double bond O, OH, because it'll go to the carboxylic acid. Make them skeletal. No, not skeletal, full structural. If the question said you've got a primary alcohol, just a primary alcohol like that, these are all H's, and you're going to add an oxidizing agent, but you're only going to distill it. So in other words, you're going to make the aldehyde, double bond O, H. That means you're going from this position to this position. You would only need 1 O, and it kicks out a water. So you're going to say plus H2O. Plus H2O down here. All right. So I'm going to redraw my oxidation of alcohols diagram, because I did sort of forget to do this when I was talking it through on videos earlier. All right. To get from here to here, you need 1 oxidizing agent. To get to the aldehyde, to get to the carboxylic acid, and if you're writing an equation, you need 2 oxidizing agents. To get to a ketone from a secondary, you need 1 oxidizing agent. But here's an extra little bit. I'm going to put plus H2O there and plus H2O there, or I might have put it in this position, in this position. So there you go. I write a little note when I send you, or underneath this video, to sort of explain that I'm going through question 6 in a lot more detail on oxidation of alcohols. Okie dokes. Right, draw a label diagram to show how you would set up the apparatus for refluxing. Well, reflux is typically a pear-shaped flask. Then what you do is you draw a line, preferably with a ruler and a pencil. This is to show a Liebig condenser. A Liebig condenser. You can just call it a condenser, because that's easy to spell than Liebig. That goes there to there. Then you draw this one around the outside. Practice this. It's really easy and it's nice, easy marks. Water goes in there. Water goes out there. You'd never draw a Bunsen burner in an exam. You just write heat. I'm going to put... Right. Anti-bumping granules. Anti-bumping granules. My dad had a sister called Bumping Granules. Then flask with condenser vertically above it. So I'd call this a pear-shaped flask. Pear-shaped flask. I'd call this a condenser. If I was confident, I think it was Liebig. Not sure about the spelling. You'll have to Google that, but it's a Liebig condenser. I think I would put water in, water out. Let's have a little look. The condenser must have an outer tube for water that is sealed. An outer tube for water that is sealed at top and bottom. Oh, yeah, that's fine. Condenser must have 2 openings for water in and out. Condenser must have an outer tube for water is sealed at top and bottom. Condenser must have 2 openings for water in and out. Okay, cool. Penalise M1 if the apparatus is sealed. If you put a lid on top, that's really dangerous because you're going to heat this and it'll build up the pressure and it'll explode. So anyway, that's worth 2 marks. That's how you draw reflux. So you heat it up, it evaporates, but as it comes up the condenser, it cools and it dribbles back down, drip, 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 and drips back in and goes round and round and round and round. Anti-bumping granules are placed in the flask when refluxing. Suggests why these granules prevent bumping. You have to you think, oh, they just stop it bumping. Well, bumping is like sudden large bubbles forming, so it prevents large bubbles. It says that in the mark scheme. Draw the structure prevents large bubbles forming. Draw the structure of a different organic product formed when acidified potassium dichromate is not in excess. All right, so here was the starting material, and what we said is if you add 3 lots of oxygen to this, 3 lots of oxidizing agent, this isn't the answer by the way, just reminding you, what will happen is this one will form a carboxylic acid and this one will form a ketone. That's what we've just done on the previous page. Well, if you didn't have enough oxidizing agent, maybe only 2 lots of oxidizing agent, well, what might happen? Well, you could form this one, where you form an aldehyde and the ketone. You could form this one, maybe just the secondary gets oxidized and the primary doesn't. You could form, which other one? You could form an aldehyde here and an OH here. You could form, and this one doesn't get oxidized. What's the final combination maybe? You could form, this one could go to carboxylic acid and this one remains untouched. All right, so there's loads of there. You can use skeletal or full structural. So anyway, there we go. Next, question 7. Loads of organic here. The alkene 3-methylpent-2-ene reacts with hydrogen bromide, that's HBr. Right, so we're dealing with an alkene and HBr, we're dealing with electrophilic addition, aren't we? To form a mixture of 3-bromo-3-methylpentane and 2-bromo-3-methylpentane. The alkane 3-methylpent-2-ene exists as E and Z isomers. Draw the Z isomer. Right, I always start off with that. And I remember that Z is on Z same side. So the large groups are on Z same side. So I'm going to put my large groups just on the top. So I'm looking at this carbon-carbon here. So this carbon-carbon has got a hydrogen and a CH3. So I'll go the light group there and the CH3 at the top. It doesn't say any particular type of structure, so this will do. And then on this side, I've got a CH3 on one side and a CH2, CH3 on the other. So I'm going to put the CH3 there and the CH2, CH3 here. So I've got the heavy up here and the heavy one up here and the light one down here and the light one down here. Then it's going to remind myself, Z same side. Yes, and there we go. Just checked it and it's correct. So that's only worth 1 mark. So don't muck that up. Right. Name and outline the mechanism for the formation of 3-bromo. 7 marks. Sweet. Should be able to smash this. Alright, I haven't even read it yet. But it should be fine, shouldn't it? Name and outline the mechanism for the formation of 3-bromo, 3-methylpentane from this reaction of 3-methylpent-2-ene with hydrogen bromide. You know what? I'm going to just draw this out. Because I know, alkene mechanism is electrophilic addition. It just is. CH2, CH3. I'm going to draw the CH3 there. Just going to draw it like I've done above. CH3 there and then H. Right. And it's forming 3-bromo, 3-methylpentane. So I might just draw that down here. How much space have I got? Does this get another page? You just get that one little bit of space. Okay, 3-methylpent-2-ene. 3-methylpent-2-ene. 3-methyl. Explain why 3-bromo, 3-methylpentane. For the formation, sorry, I wasn't reading that right. I got a bit distracted. I got a text message come through. 3-bromo, 3-methyl. 3-bromo. 3-methyl pentane. So that's what I'm doing first. I'm just making sure I've drawn the starting material and the end product. So what's happening, right, is if you have a look along here, this carbon, I'm just going to mark that is that carbon, this carbon is that carbon, this carbon is that carbon. There's a CH3, I've put it up at the top, and there's a CH2, CH3 there. It's an alkene, you're going to be adding H and Br across it. So, mechanism, H, Br, curly arrow from there, curly arrow to there. I'm just going to join that on, delta positive, delta negative. This will form C, C. I'm going to put everything in that doesn't get affected. CH3, I'm going to move that H around a little bit. CH2, CH3, and CH3 there. Now I've just got to decide which one is the H bonded to and which one is the carbocation. I'll look below for that. The carbocation is going to be here in position 3. So that's going to have an H on it. So this H here is this H here. Alright, I've then got a Br minus with a lone pair. It's going to attack to that carbon. That's that. Okay, right, what's the next bit? Explain why more 3-bromo 3-methyl pentane. So explain why you get more of this than 2-bromo 3-methyl pentane than 1, 2, 3, 4, 5. Then this. You don't have to draw this, sorry. You don't have to draw this. Okay, in fact, there's no reason to at all. But it might just help with your understanding, I suppose. Right, the reason you get more of this, in other words, that this is the major product and this is the minor product, is because this one, which is, give it its name, 2-bromo 3-methyl pentane, is formed via a secondary carbocation, whereas this one is formed via a tertiary carbocation, and tertiary carbocations are more stable than secondary. Alright, so 1 mark for this, 1 mark for the talk about stability, tertiary more stable than secondary, 4 marks for the mechanism. Oh, it's so straightforward though. You should be scoring highly on that. But no, you're probably not, because it's horrible when a teacher says it's so straightforward. But you know what I'm saying, don't you? At the time, it was easy for you. Alright, so you've got to remember that. Right, this looks fairly tricky. God, I'm even going to get onto the multi-choice. God knows. When an aqueous solution of ethanoic acid reacts with magnesium, ethanoic acid, might not even need this, but I'm just showing you that I know me stuff, and it's good to just know what's going on. Reacts with magnesium. So that's an acid plus metal. Metal plus acid makes salt plus hydrogen. The progress of the reaction can be followed by using equipment to measure the volume of hydrogen produced. Told ya, H2. Figure 6 shows how the volume of hydrogen produced varies with time. When 363 milligrams of magnesium, moles alert, so you can work out moles of that later, are added to 30 centimeters cubed of this much ethanoic acid, moles alert, because you've got a volume and a concentration. Alright, there's a graph. Let's see what we have to do with it. I imagine I'm going to be having 2 pages. Coming back to that graph in a minute. Right, the equation for the reaction between ethanoic acid and magnesium is shown here. So, moles, God, well, it looks really straightforward, this. Moles of magnesium, well, you got 396 milligrams, that's 0.396 grams of magnesium mass divided by the MR divided by 24.3, that equals 0.136 moles of magnesium. I've got 163 moles of magnesium. No, I haven't. I've got 0.0163 moles of magnesium. Moles of this, the way I tend to do it is CV divided by 1,000. I know Dr. Holliday does C. You do the conversion of the volume first, but I do CV divided by 1,000 or 30 divided by 1,000 times 0.6. Anyway, that's 0.018 moles. So which one of these is in excess? Well, I should have put that note in there, sorry. 0.0163 or 0.018. The way I like to do this, I need 2 of these for every one of these. So I cover up one of them and I say, if I've got 0.018 of this, I need 0.009. Oh, I'm going to cover that up again, sorry. There's me 2 volumes. So the way I do it, I say if I've got 2 of these, I need 1 of these. So if I've got 0.018, I cover it up and I say I would need 0.009. Have I got 0.009? I've got more than enough. More than enough. There's another word for that. That means you've got excess. This is the excess. All right. And it's in excess because you could say something like to completely react 0.018 moles of CH3COOH, you need 0.009 moles of Mg, but you've got this many more moles. Whatever. Okay. The reaction was repeated using 20 centimeters cubed of 0.8 moles per decimeter cubed ethanoic acid, with all of the other conditions the same. The magnesium was still in excess. Sketch a line on figure 6 to show how the volume of hydrogen produced varies with time in this second experiment. Alright, so what was the first experiment then? The first experiment, so experiment 1 was, where are we now? Lost my other sheet. Is it on the back of here? Where have I put that now? I've took the mouse key. Experiment 1 was 0.6, that's the concentration, and you had 30 centimeters cubed. Experiment 2 was 0.8, and you've got 20 centimeters cubed. So what I'm going to do with that then is I've got to decide firstly, is it going to react faster or slower? Well, this second experiment is at a higher concentration, so you're going to get right, let's work out the moles first. 0.8. So in this one I had 0.018 moles because I did C times V over 1,000. In the second experiment I've got 0.016 moles, but they're in a smaller volume, it's more concentrated. So that more concentrated acid will mean that I'm going to produce the gas more quickly. Where is that graph? Because I need to draw on it now. Oh, there it is. Underneath here. Alright, so I'm pretty sure it's going to start off steeper. But I'm not going to make as much hydrogen. Why am I not going to make as much hydrogen? The magnesium's in excess. Alright, yeah. The magnesium's in excess, so that's not that important. So in this experiment, if you add 0.018 moles of this, you're going to make 2 to 1, 0.009 moles of hydrogen. In this second experiment that we do, we've got 0.016 moles. The magnesium's still in excess, so it has no bearing. So you're going to make 0.008 moles of hydrogen. This graph hasn't got any axes on, so I'm hoping this is going to be 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, it's 9 up. So the second one needs to finish here. So I think it's going to go faster because it's a higher concentration. And it's going to finish there. Mark scheme. Line starts at origin and is steeper. Yes. Moles is 0.16, so it levels out on the 8th line. I think that's quite hard. You can hear I was floundering a bit with it. But the questions get harder through the paper, and there's been loads of tough ones. Loads of easy ones, sorry. So, yeah, no. Right. I'm going to stop there, and I'm going to do MultiChoice separately. So I know I said there'd only be 3 videos, but I'm changing my mind. Right, bye.